Chapter 8. Optoelectronic devices. Objectives. 1. Understand solar cells. 2. Study photodetectors such as avalanche photodiodes. 3. Study incoherent light sources, LEDs, and coherent light sources, lasers. So far we have primarily concentrated on electronic devices. There is also a wide variety of very interesting and useful device functions involving the interaction of photons with semiconductors. These devices provide the optical sources and detectors that allow broadband telecommunications and data transmission over optical fibers. This important area of device applications is called optoelectronics. In this chapter we will discuss devices that detect photons and those that emit photons. Devices that convert optical energy into electrical energy include photodiodes and solar cells. Emitters of photons include incoherent sources such as light-emitting diodes, LEDs, and coherent sources in the form of lasers. In section 4.3.4 we saw that bulk semiconductor samples can be used as photoconductors by providing a change in conductivity proportional to an optical generation rate. Often, junction devices can be used to improve the speed of response and the sensitivity of detectors of optical or high-energy radiation. Two-terminal devices designed to respond to photon absorption are called photodiodes. Some photodiodes have extremely high sensitivity and response speed. Since modern electronics often involves optical as well as electrical signals, photodiodes serve important functions as electronic devices. In this section, we shall investigate the response of p-n junctions to optical generation of electron-hole pairs, EHPs, and discuss a few typical photodiode detector structures. We shall also consider the very important use of junctions as solar cells, which convert absorbed optical energy into useful electrical power. Current and voltage in an illuminated junction. In Chapter 5 we identified the current due to drift of minority carriers across a junction as a generation current. In particular, carriers generated within the depletion region W are separated by the junction field, electrons being collected in the N region and holes in the P region. Also, minority carriers generated thermally within a diffusion length of each side of the junction diffuse to the depletion region and are swept to the other side by the electric field. If the junction is uniformly illuminated by photons with HNEG, an added generation rate GOP, electron-hole pairs per cubic centimeter, participates in this current, Fig 8.1. The number of holes created per second within a diffusion length of the transition region on the N side is ALP-GOP. Similarly ALN-GOP electrons are generated per second within LNOF XP0 and AO-GOP carriers are generated within W. The resulting current due to the collection of these optically generated carriers by the junction is. If we call the thermally generated current described in EQ 537b, ith, we can add the optical generation of EQ 8.1, to find the total reverse current with illumination. Since this current is directed from N to P, the diode equation EQ 536 becomes. Thus the current voltage curve is lowered by an amount proportional to the generation rate, Fig 8.1c. This equation can be considered in two parts: the current described by the usual diode equation and the current due to optical generation. When the device is short-circuited, V equals 0, the terms from the diode equation cancel in EQ 8.2, as expected. However, there is a short-circuit current from N to P equal to I. Figure 8.1 Optical generation of carriers in a p-n junction, A. Absorption of light by the device, B. Current I-op resulting from electron-hole pair generation within a diffusion length of the junction on the N side, C. Current voltage characteristics of an illuminated junction. Thus the current voltage characteristics of Fig 8.1c cross the I-axis at negative values proportional to GOP. When there is an open circuit across the device, I equals 0 and the voltage V equal VOC is. For the special case of a symmetrical junction, number of holes equals number of electrons and hole lifespan equals electron lifespan, we can rewrite EQ 8.3a in terms of the thermal generation rate PNTN equal GTH and the optical generation rate GOP. Neglecting generation within W. Actually, the term GTH equal PNTN represents the equilibrium thermal generation recombination rate. As the minority carrier concentration is increased by optical generation of electron-hole pairs, the lifetime Tn becomes shorter, and becomes larger. Pn is fixed, for a given concentration of donors and temperature. Therefore, Voc cannot increase indefinitely with increased generation rate. In fact, the limit on Voc is the equilibrium contact potential V0, Fig. 8.2. This result is to be expected, since the contact potential is the maximum forward bias that can appear across a junction. The appearance of a forward voltage across an illuminated junction is known as the photovoltaic effect. Depending on the intended application, the photodiode of Fig. 8.1 can be operated in either the third or fourth quarters of its current voltage characteristic. As Fig. 8.3 illustrates, power is delivered to the device from the external circuit when the current and junction voltage are both positive or both negative, first or third quadrants. In the fourth quadrant, however, the junction voltage is positive and the current is negative. In this case, power is delivered from the junction to the external circuit. Notice that in the fourth quadrant the current flows from the negative side of V to the positive side, as in a battery. Figure 8.2 Effects of illumination on the open circuit voltage of a junction. A. Junction at equilibrium. B. Appearance of a voltage Voc with illumination. Figure 8.3 Operation of an illuminated junction in the various quadrants of its current voltage characteristic. In A and B, power is delivered to the device by the external circuit. In C, the device delivers power to the load. If power is to be extracted from the device, the fourth quadrant is used. On the other hand, in applications as a photodetector, we usually reverse bias the junction and operate it in the third quadrant. We shall investigate these applications more closely in the discussion to follow. For steady-state optical excitation, we can write the hole diffusion equation as: assume that a long P plus N diode is uniformly illuminated by an optical signal, resulting in GOP electron-hole pairs per cubic centimeter. Calculate the hole diffusion current IP, Xn, and evaluate it at Xn equals 0. Compare the result with EQ. 8.2, evaluated for a P plus at N junction. The last equation corresponds to EQ. 8.2, for number of electrons less than number of holes, except that the component due to generation on the P side is not included. Solar cells. Since power can be delivered to an external circuit by an illuminated junction, it is possible to convert solar energy into electrical energy. If we consider the fourth quadrant of Fig. 8.3c, it appears doubtful that much power can be delivered by an individual device. The voltage is restricted to values less than the contact potential, which in turn is generally less than the band gap voltage Eg/Q. For silicon, the voltage Voc is less than about 1 V. The current generated depends on the illuminated area, but typically IOP is in the range 10-100 mA for a junction with an area of about 1 square centimeter. However, if many such devices are used, the resulting power can be significant. In fact, arrays of PN junction solar cells are currently used to supply electrical power for many space satellites. Solar cells can supply power for the electronic equipment aboard a satellite over a long period, which is a distinct advantage over batteries. The array of junctions can be distributed over the surface of the satellite or can be contained in solar cell paddles attached to the main body of the satellite, Fig. 8.4a. A 72 MW solar cell plant in Italy is shown in Fig. 8.4b. To utilize a maximum amount of available optical energy, it is necessary to design a solar cell with a large area junction located near the surface of the device, Fig. 8.5. The planar junction is formed by diffusion or ion implantation, and the surface is coated with appropriate materials to reduce reflection and to decrease surface recombination. Many compromises must be made in solar cell design. In the device shown in Fig. 8.5, for example, the junction depth D must be less than LP in the N material to allow holes generated near the surface to diffuse to the junction before they recombine. Similarly, the thickness of the P region must be such that electrons generated in this region can diffuse to the junction before recombination takes place. This requirement implies a proper match between the electron diffusion length Ln, the thickness of the P region, and the mean optical penetration depth 1/ACEQ. 4.2. It is desirable to have a large contact potential V0 to obtain a large photovoltage, and therefore heavy doping is indicated. On the other hand, long lifetimes are desirable and these are reduced by doping too heavily. Figure 8.4. A. Solar cell arrays attached to the International Space Station. The solar array wings measure 74 m tip to tip. Each wing contains 32,800 solar cells and can produce 62 kilowatts of power for the station. Courtesy of NASA. B. 72MW terrestrial solar plant in Italy. Courtesy of MEMC/Sun Edison. Figure 8.5 Configuration of a solar cell. A. Enlarged view of the planar junction. B. Top view, showing metal contact fingers. It is important that the series resistance of the device be very small so that power is not lost to heat due to ohmic losses in the device itself. A series resistance of only a few ohms can seriously reduce the output power of a solar cell. Prob 8.7. Since the area is large, the resistance of the P-type body of the device can be made small. However, contacts to the thin N region require special design. If this region is contacted at the edge, current must flow along the thin N region to the contact, resulting in a large series resistance. To prevent this effect, the contact can be distributed over the N surface by providing small contact fingers as in Fig 8.5b. These narrow contacts serve to reduce the series resistance without interfering appreciably with the incoming light. Figure 8.6 Current voltage characteristics of an illuminated solar cell. The maximum power rectangle is shaded. Figure 8.6 shows the fourth quadrant portion of a solar cell characteristic, with IR plotted upward for the convenience of illustration. The open circuit voltage VOC and the short circuit current ISC are determined for a given light level by the cell properties. The maximum power delivered to a load by this solar cell occurs when the product VIR is a maximum. Calling these values of voltage and current VM and IM, we can see that the maximum delivered power illustrated by the shaded rectangle in Fig 8.6 is less than the ISC-VOC product. The ratio IM/VM/ISC-VOC is called the fill factor, and is a figure of merit for solar cell design. Applications of solar cells are not restricted to outer space. It is possible to obtain useful power from the sun in terrestrial applications using solar cells, even though the solar intensity is reduced by the atmosphere. Current worldwide total power generation capability is 15 terawatts and corresponds to an annual energy usage of 500 quads, 1 quad equal 1015, or a quadrillion, BTU, with an annual increase of 1 to 2. Of this, 80 comes from fossil fuels, oil, natural gas, and coal, which will be exhausted in several hundred years. In addition, carbon dioxide emissions and global warming have spurred a renewed interest in green sources of free energy such as photovoltaics, of which the current installed capacity worldwide is about 100 gigawatts. About 1 kilowatt per square meter is available in a particularly sunny location, translating to about 600 terawatts potentially available worldwide, but not all of this solar power can be converted to free electricity. Much of the photon flux is at energies less than the cell band gap and is not absorbed. High-energy photons are strongly absorbed, and the resulting electron-hole pairs may recombine at the surface. A well-made single-crystal silicon cell can have about 25 efficiency for solar energy conversion, providing 250 watts per square meter of electrical power under full illumination. This is a modest amount of power per unit solar cell area, considering the cost and effort involved in fabricating a large area of silicon cells. Amorphous silicon thin-film solar cells can be made more cheaply, but have lower efficiencies, 10, because of the defects in the material. The cost and scalability of photovoltaic technology are of paramount importance for terrestrial applications. Currently, it costs only about 3 cents per kilowatt-hour for electricity generation from fossil fuels, but about 10 times that amount from amorphosilicon solar cells, and the time to recover the investment in photovoltaics is about 4 years. In terms of scalability, at 10% cell efficiency, approximately 3% of the land area would have to be covered with solar cells to meet U.S. energy needs, which would, of course, create other environmental problems. One approach to obtaining more power per cell is to focus considerable light onto the cell with the use of mirrors. Although silicon cells lose efficiency at the resulting high temperatures, gallium arsenide and related compounds can be used at 100 degrees Celsius or higher. In such solar concentrator systems, more effort and expense can be put into the solar cell fabrication, since fewer cells are required. For example, a gallium arsenide aluminum gallium arsenide heterojunction cell provides good conversion efficiency and operates at the elevated temperatures that are common in solar concentrator systems. In such systems, the area required is shifted from the cell to the concentrator. A silicon solar cell has a short circuit current of 100 mA and an open circuit voltage of 0.8 volts under full solar illumination. The fill factor is 0.7. What is the maximum power delivered to a load by this cell? Photodetectors. When the photodiode is operated in the third quadrant of its current voltage characteristic, Fig 8.3b, the current is essentially independent of voltage but is proportional to the optical generation rate. Such a device provides a useful means of measuring illumination levels or of converting time-varying optical signals into electrical signals. In most optical detection applications, the detector's speed of response, or bandwidth, is critical. For example, if the photodiode is to respond to a series of light pulses 1 nanoseconds apart, the photo-generated minority carriers must diffuse to the junction and be swept across to the other side in a time much less than 1 nanoseconds. The carrier diffusion step in this process is time-consuming and should be eliminated if possible. Therefore, it is desirable that the width of the depletion region W be large enough so that most of the photons are absorbed within W rather than in the neutral P and N regions. When an electron-hole pairs is created in the depletion region, the electric field sweeps the electron to the N side and the hole to the P side. Since this carrier drift occurs in a very short time, the response of the photodiode can be quite fast. When the carriers are generated primarily within the depletion layer width, the detector is called a depletion layer photodiode. Obviously, it is desirable to dope at least one side of the junction lightly so that W can be made large. Figure 8.7 Schematic representation of a PIN photodiode. The appropriate width for W is chosen as a compromise between sensitivity and speed of response. If W is wide, most of the incident photons will be absorbed in the depletion region, leading to a high sensitivity. Also, a wide W results in a small junction capacitance CEQ. 562, thereby reducing the RC time constant of the detector circuit. On the other hand, W must not be so wide that the time required for drift of photo-generated carriers out of the depletion region is excessive, leading to low bandwidth. One convenient method of controlling the width of the depletion region is to build a PIN photodetector, Fig 8.7. The I region need not be truly intrinsic, as long as the resistivity is high. It can be grown epitaxially on the N-type substrate, and the P region can be obtained by implantation. When this device is reverse biased, the applied voltage appears almost entirely across the I region. If the carrier lifetime within the I region is long compared with the drift time, most of the photo-generated carriers will be collected by the N and P regions. An important figure of merit for a photodetector is the external quantum efficiency HQ, defined as the number of carriers that are collected for every photon impinging on the detector. For a photocurrent density JOP, we collect JOP Q carriers per unit area per second. For an incident optical power density of POP, the number of photons shining on the detector per unit area per second is pop/HV. Therefore, for a photodiode that has no current gain, the maximum HQ is unity. If low-level optical signals are to be detected, it is often desirable to operate the photodiode in the avalanche region of its characteristic. In this mode, each photo-generated carrier results in a significant change in the current because of avalanche multiplication, leading to gain and external quantum efficiencies of greater than 100%. Avalanche photodiodes, APDs, are useful as detectors in fiber optic systems, section 8.2.2. The type of photodiode described here is sensitive to photons with energies near the bandgap energy, intrinsic detectors. If Hn is less than Eg, the photons will not be absorbed. On the other hand, if the photons are much more energetic than Eg, they will be absorbed very near the surface, where the recombination rate is high. Therefore, it is necessary to choose a photodiode material with a bandgap corresponding to a particular region of the spectrum. Detectors sensitive to longer wavelengths can be designed such that photons can excite electrons into or out of impurity levels, extrinsic detectors. However, the sensitivity of such extrinsic detectors is much less than intrinsic detectors, where electron-hole pairs are generated by excitation across the bandgap. By using lattice-matched multilayers of compound semiconductors, the bandgap of the absorbing region can be tailored to match the wavelength of light being detected. Wider bandgap material can then be used as a window through which the light is transmitted to the absorbing region, Fig 8.8. For example, we saw in Fig 113 that indium gallium arsenide with an in-mole fraction of 53, can be grown epitaxially on indium phosphide with excellent lattice matching. This composition of indium gallium arsenide has a bandgap of about 0.75 electron volts, which is sensitive to a useful wavelength for fiber optic systems, 1.55 micrometers, as we shall see in section 8.2.2. In making a photodiode using indium gallium arsenide as the active material, it is possible to bring the light through the wider bandgap indium 0.52 aluminum 0.48 arsenide, also lattice matched to indium phosphide, thus greatly reducing surface recombination effects. In the case of avalanche photodiodes requiring narrow bandgap material, it is often advantageous to absorb the light in the narrowgap semiconductor, for example, indium gallium arsenide, and transport the resulting carriers to a junction made in wider bandgap material, for example, indium aluminum arsenide, where the avalanche multiplication takes place at high fields. Such a separation of the absorption and multiplication avalanche photodiodes avoids the excessive leakage currents typical of reverse-biased junctions in narrowgap materials. In this particular structure, there is also a doped indium aluminum arsenide charge layer, leading to a SACM avalanche photodiodes, which helps optimize, decrease, the electric field further between the multiplication and absorption regions. In certain avalanche photodiodes, one can grade the alloy composition between the high bandgap multiplication regions and the lower bandgap absorption region to avoid any band edge discontinuities, which can trap photo-generated carriers. The photocurrent and dark current both increase with bias because of avalanche multiplication, Fig 8.8b. One obviously wants to maximize the difference I between the photocurrent IP and the dark current ID. The ratio of I at different voltages to that at a low reference voltage is defined as the gain of the avalanche photodiodes. Gain, bandwidth, and signal-to-noise ratio of photodetectors. In optical communication systems, the sensitivity, which depends on gain, of the photodetector and its response time, bandwidth, are of critical importance. Typical gain bandwidth characteristics of such a SACM APD are shown in Fig 8.8c and are limited by the transit time of carriers through the structure. Unfortunately, designs that increase gain tend to decrease bandwidth and vice versa. It is common to express the gain bandwidth product as a figure of merit for detectors. In a PIN diode, there is no gain mechanism, since at most one electron hole pairs is collected by the junction for each photon absorbed. Thus, the gain is essentially unity, and the gain bandwidth product is determined by the bandwidth, or frequency response. Figure 8.8 Use of multi-layer heterojunctions to enhance the photodiode operation. An avalanche photodiode in which light near 1.55 micrometers is absorbed in a narrow bandgap material, indium gallium arsenide, e.g. equals 0.75 electron volts, after passing through a wider gap material, indium phosphide and indium aluminum arsenide, electrons are swept to an indium aluminum arsenide junction, where avalanche multiplication takes place. The I regions are lightly doped, B, photocurrent, dark current, and gain increasing as a function of bias because of avalanche multiplication. C, typical gain bandwidth characteristics of such a SACM avalanche photodiode. In a PIN, the response time is dependent on the width of the depletion region. Another important property of detectors is the signal-to-noise, S/N, ratio, which is the amount of usable information compared with the background noise in the detector. In the case of photoconductors, the major source of noise is random thermal motion of the carriers, leading to fluctuations in the dark current, called Johnson noise. The noise current increases with temperature, and with the conductance of the material in the dark. Therefore, the photoconductor noise at a given temperature can be reduced by increasing the dark resistance. Yet another source of noise at low frequencies is 1/F or flicker noise, due to carrier trapping and detrapaging at defects. In a PIN diode, the dark current is smaller and the dark resistance much higher than in a photoconductor, and the main source of noise is random thermal generation recombination of electron-hole pairs within this region, called shot noise. The shot noise is ultimately due to the quantization of the charge of electrons and holes. The noise in a PIN device is considerably lower than that in a photoconductor, as well as in avalanche photodiodes, for reasons described next. Avalanche photodiodes have the advantage of providing gain through the avalanche multiplication effect. The disadvantage is increased noise relative to the PIN, due to random fluctuations in the avalanche process. This noise is reduced if the impact ionization in the high field region is due to only one type of carrier, since more fluctuations in the ionization process occur when both electrons and holes participate. In silicon, the ability of electrons to create electron-hole pairs in an impact ionization event is much higher than for holes. Therefore, silicon avalanche photodiodes can be operated with high gain and relatively low noise. Unfortunately, silicon avalanche photodiodes cannot be used for most fiber optic transmission because silicon is transparent at the wavelengths of low loss and low dispersion, L equal 1.55 and 1.3 micrometers, for optical fibers. For these longer wavelengths, indium 0.53 gallium 0.47 arsine has become the material of choice. However, the ionization rates of electrons and holes in most compound semiconductors are comparable, which degrades their noise and frequency response relative to silicon avalanche photodiodes. The various sources of noise determine the S/N ratio in a photodetector. One quantifies it as a noise equivalent power, NEP, which is the minimum detectable signal that would produce the same RMS output as the noise. The detectivity of the photodetector is then defined as D equal 1/NEP. The NEP depends on the area of the photodetector as well as the bandwidth. The specific detectivity, D*, is then defined as that for a detector of unit area and a bandwidth of 1 Hz. Clearly, once the bandwidth requirements are met, it is desirable to choose a photodetector with the highest D*. Another approach that has demonstrated excellent performance in terms of both high sensitivity and bandwidth utilizes a waveguide structure, Fig 8.9. Here, unlike the situation with the PIN photodiode, Fig 8.7, or the avalanche photodiode, Fig 8.8, the light strikes the photodiode perpendicular to the current transport. The advantage is that now the absorption region can be made quite long, along the photon path, leading to high sensitivity, while at the same time the photo-generated carriers have to traverse a short distance in the perpendicular direction, leading to short transit times and high bandwidth. Figure 8.9 Schematic of a waveguide photodiode. The photons are strongly absorbed in the narrow bandgap indium gallium arsenide region A, and carriers are multiplied by the avalanche process in region M. The charge region C helps optimize the electric field profile between A and M. When carriers are injected across a forward-biased junction, the current is usually accounted for by recombination in the transition region and in the neutral regions near the junction. In a semiconductor with an indirect band gap, such as silicon or germanium, the recombination releases heat to the lattice. On the other hand, in a material characterized by direct recombination, considerable light may be given off from the junction under forward bias. This effect, called injection electroluminescence, section 4.2.2, provides an important application of diodes as generators of light. The use of LEDs in digital displays is well known. There are also other important applications, in traffic and automotive signals and in illumination. Another important device making use of radiative recombination in a forward-biased p-n junction is the semiconductor laser. As we shall see in section 8.4, lasers emit coherent light in much narrower wavelength bands than LEDs, with more collimation, directionality, and are very useful for fiber optic communication systems, as described in section 8.2.2. For LEDs, the frequency, color, of the photon is governed by the band gap of the semiconductor as given by the Planck relation, Hn equal Eg, which, in appropriate units, can be expressed as Eg, electron volts, equal 124/L, micrometers. A very important metric of an LED is the external quantum efficiency Hext, which is defined as the light output divided by the electrical input power, Hext equal, internal radiative efficiency, asterisk, extraction efficiency, 8.5. The internal efficiency is a function of the quality of the material and the structure and composition of the layer. Defects in the material will clearly lead to non-radiative recombination. However, even if the internal efficiency is high, not all emitted photons are extracted from the LED. The emitted photons from an LED have a wide angular distribution, unlike those in a laser. For example, if an LED had a planar surface, the photons incident on the semiconductor-air interface at angles greater than a critical angle would undergo total internal reflection and ultimately be lost via absorption within the semiconductor. Hence, typically, LEDs are made with a dome-type encapsulation, which acts as a lens so that more of the photons can be extracted. Light-emitting materials. The band gaps of various binary compound semiconductors are illustrated in Fig 4.4 relative to the spectrum. There is a wide variation in band gaps and, therefore, in available photon energies, extending from the ultraviolet, gallium nitride, 3.4 electron volts, into the infrared, indium antimonide, 0.18 electron volts. In fact, by utilizing ternary and quaternary compounds, the number of available energies can be increased significantly, see Figs 1.13 and 3.6. A good example of the variation in photon energy obtainable from the compound semiconductors is the ternary alloy gallium arsenide phosphide, which is illustrated in Fig 8.10. When the percentage of arsine is reduced and phosphor is increased in this material, the resulting band gap varies from the direct 1.43 electron volt gap of gallium arsenide, infrared, to the indirect 2.26 electron volt gap of gallium phosphide, green. The band gap of gallium arsenide 1x phosphide X varies almost linearly with X until the 0.45 composition is reached, and electron-hole recombination is direct over this range. The most common alloy composition used in red LED displays is X0.4. For this composition the band gap is direct, since the G minimum, at K equals 0, is the lowest part of the conduction band. This results in efficient radiative recombination, and the emitted photons, 1.9 electron volts, are in the red portion of the spectrum. For gallium arsenide 1x phosphide X with phosphor concentrations above 45%, the band gap is due to the indirect X minimum. Radiative recombination in such indirect materials is generally unlikely, because electrons in the conduction band have different momentum from holes in the valence band, see Fig 3.5. Interestingly, however, indirect gallium arsenide 1X phosphide X, including gallium phosphide, X equal 1, doped with nitrogen can be used in LEDs with light output in the yellow to green portions of the spectrum. This is possible because the nitrogen impurity binds an electron very tightly. This confinement in real space, X, means that the electron momentum is spread out in momentum space P by the Heisenberg uncertainty principle CEQ. 218. As a result, the momentum conservation rules, which generally prevent radiative recombination in indirect materials, are circumvented. Thus nitrogen doping of gallium arsenide 1X phosphide X is not only useful technologically, but also provides an interesting and practical illustration of the uncertainty principle. In many applications, light from a laser or an LED need not be visible to the eye. Infrared emitters such as gallium arsenide, indium phosphide, and mixed alloys of these compounds are particularly well suited to fiber optical communication systems or TV remote controls. For example, a laser or LED can be used in conjunction with a photodiode or other photosensitive device to transmit information optically between locations. Figure 8.10 Conduction band energies as a function of alloy composition for gallium arsenide 1X phosphide X. By varying the current through the diode, the light output can be modulated such that analog or digital information appears in the optical signal directed at the detector. Alternatively, the information may be introduced between the source and detector. For example, a semiconductor laser photodetector arrangement can be used in a compact disc or DVD system for reading digital information from the spinning disc. A light emitter and a photodiode form an optoelectronic pair, which provides complete electrical isolation between input and output, since the only link between the two devices is optical. In an optoelectronic isolator, both devices may be mounted on a ceramic substrate and packaged together to form a unit that passes information while maintaining isolation. Figure 8.11 Improvement of luminous intensity of LEDs over time. In view of the broad range of applications requiring semiconductor lasers and LEDs with visible and infrared wavelengths, the wide variety of available 3,5 materials is extremely useful. In addition to the aluminum gallium arsenide and gallium arsenide phosphide systems shown in Fig 3.6 and Fig 8.10, the indium aluminum gallium phosphide system is useful for red, yellow, and orange wavelengths, and aluminum gallium indium nitride is a strong emitter in the blue and green. Why is there so much interest in short wavelength emitters such as blue-green LEDs as shown in Fig 8.11, moderate efficiency, 10 lumens per watt, red, green, and yellow-green LEDs have existed for a long time in the gallium arsenide phosphide system, based on concepts such as N-isoelectronic doping. More recently, in the mid-1990s, much higher brightness and efficiency, 30 lumens per watt, red-orange-yellow LEDs based on the indium aluminum gallium phosphide system have been developed. The higher bandgap indium aluminum gallium nitride system has direct band gaps over the entire alloy composition range and hence offers highly efficient light emission in the blue and green part of the spectrum. A major goal of the optoelectronics community has been the achievement of high-efficiency red, green, and blue emitters, because those colors are the three primary colors of the spectrum. By combining these color LEDs, or in conjunction with suitable phosphors, one can form intense white light sources, 500 lumens, with luminous efficiencies 2 times greater than those of conventional incandescent light bulbs. Since general-purpose illumination typically requires kilolumens of light, it may be practical to combine a few of these high-brightness LEDs for that purpose. They also have much longer lifetimes, 5,100, 000 hours versus 2,000 hours for conventional light bulbs, and much higher energy efficiencies. The costs of these LEDs have been reduced considerably in recent years, making them more competitive. Continued application of these LEDs in lighting can lead to a significant reduction in global energy demand. Arrays of red, green, and blue emitters are being used in outdoor displays and TV screens, as well as in automotive taillights and signal lights. Red, yellow, and green LEDs are being used for traffic lights because they have a much higher reliability and lifetime than conventional light bulbs, and they save energy. For many years an efficient blue emitter was elusive, because materials with wide band gap also tend to require crystal growth at high temperatures. Therefore, they are difficult to grow on convenient substrates. An excellent candidate in terms of band gap is gallium nitride, which has Eg corresponding to the ultraviolet. Unfortunately, deposition of gallium nitride by MOCVD or other methods requires a substrate that can withstand high temperatures. A convenient substrate is sapphire, which has a melting point above 2000 degrees Celsius. However, there is considerable lattice mismatch between sapphire and gallium nitride, and epitaxial gallium nitride films suffer from dislocations that thread from the sapphire gallium nitride interface through the film. These threading dislocations can serve as non-radiative electron-hole pair recombination sites where carriers recombine with their energy given up as heat rather than light. This is not good news for an lead material, and for many years gallium nitride films were inefficient light emitters. As sometimes happens, too bad it's not more often, nature provides a way around a problem that seems insurmountable. In this case it turns out that addition of In during the growth of the gallium nitride film provides a way to avoid catastrophic loss of carriers at dislocations. Since In is not completely miscible in gallium nitride, In-rich clusters form in indium gallium nitride which have a smaller band gap than the rest of the film. Therefore, carriers diffusing through the indium gallium nitride can fall into the potential well of the lower band gap cluster and recombine radiatively. If the density of such low band gap clusters significantly outnumbers the density of threading dislocations, many of the electron-hole pairs can survive to recombine giving off light. This discovery revolutionized the search for wide bandgap materials to allow light emission in the blue and violet spectra. White light can be obtained by combining red, green, and blue emitters or by coating a blue or violet emitter with phosphors that can re-emit various wavelengths to achieve white light. In recent years these white LED have been engineered to be extremely efficient, allowing the application of such high brightness LEDs in lighting applications. One problem that is faced with LEDs is that many of the photons that are generated cannot be extracted from the device if it is a planar structure. The reason is that the semiconductor has a higher refractive index than the surrounding air, medium, and for a light ray impinging on the surface at greater than the critical angle, it undergoes total internal reflection, and is reabsorbed. Hence, it is important to texture the surface of the LEDs to create microlenses such that a larger fraction of the light rays can be extracted. There are also important packaging challenges to dissipate heat from the devices by creating proper heat sinks. Therefore, considerable device engineering has been applied to the design of these devices in recent years, and the results have been impressive in terms of lumens out for a given power into the LED. Finally, after many years of work by crystal growers, device designers and packaging engineers, LEDs have become widespread in lighting as well as in displays. Fiber optic communications. The transmission of optical signals from source to detector can be greatly enhanced if an optical fiber is placed between the light source and the detector. An optical fiber is essentially a light pipe or waveguide for optical frequencies. The fiber is typically drawn from a boule of glass to a diameter of 25 micrometers. The fine glass fiber is relatively flexible and can be used to guide optical signals over distances of kilometers without the necessity of perfect alignment between source and detector. This significantly increases the applications of optical communication in areas such as telephone and data transmission. One type of optical fiber has an outer layer of very pure fused silica, silicon dioxide, with a core of germanium-doped glass having a higher index of refraction, Fig 812a. One such a step index fiber maintains the light beam primarily in the central core with little loss at the surface. The light is transmitted along the length of the fiber by internal reflection at the step in the refractive index. Figure 812. Two examples of multimode fibers: A step index having a core with a slightly larger refractive index n, B, a graded index having, in this case, a parabolic grading of n in the core. The figure illustrates the cross-section, left, of the fiber, its index of refraction profile, center, and typical mode patterns, right. Losses in the fiber at a given wavelength can be described by an attenuation coefficient A similar to the absorption coefficient of EQ. 4.3. The intensity of the signal at a distance x along the fiber is then related to the starting intensity by the usual expression. The attenuation is not the same for all wavelengths, however, and it is therefore important to choose a signal wavelength carefully. A plot of A versus L for a typical silica glass fiber is shown in Fig 8.13. It is clear that DIPs in A near 1.3 and 1.55 micrometers provide windows in the attenuation, which can be exploited to reduce the degradation of signals. The overall decrease in attenuation with increasing wavelength is due to the reduced scattering from small random inhomogeneities which result in fluctuations of the refractive index on a scale comparable to the wavelength. This type of attenuation, called Rayleigh scattering, decreases with the fourth power of wavelength. This effect is observed at sunrise and sunset, when attenuation of short wavelength blue and green light results in red and orange sunlight. Obviously, Rayleigh scattering encourages operation at long wavelengths in fiber optic systems. However, a competing process of infrared absorption dominates for wavelengths longer than about 1.7 micrometers, due to vibrational excitation of the atoms making up the glass. Therefore, a useful minimum in absorption for silica fibers occurs at about 1.55 micrometers, where epitaxial layers in the indium, gallium, arsenide, phosphate system can be grown lattice-matched to indium phosphide substrates, see Fig 1.13. Another consideration in choice of operating wavelength is the pulse dispersion, or spreading of data pulses as they propagate down the fiber. Figure 8.13 typical plot of attenuation coefficient A versus wavelength L for a fused silica optical fiber. Peaks are due primarily to O impurities. This effect can be caused by the wavelength dependence of the refractive index, causing different optical frequencies to travel down the fiber with slightly different velocities. This effect, called chromatic dispersion, is much less pronounced at the 1.3 micrometer window in Fig 8.13. Another cause of dispersion is the fact that different modes propagate with different path lengths, Fig 8.12a. This type of dispersion can be reduced by grading the refractive index of the core, Fig 8.12b, such that various modes are continually refocused, reducing the differences in path lengths. The light source in a fiber optic system today is a laser, because the light is made up of essentially a single frequency and allows a very large information bandwidth. Semiconductor lasers suitable for fiber optic communications will be discussed in section 8.4. In early optoelectronic systems for fiber optics, it was most convenient to use the well-established gallium arsenide aluminum gallium arsenide system for making lasers and LEDs. These light sources are highly efficient, and good detectors can be made using silicon PIN or avalanche photodiodes. However, these sources operate in the wavelength range near 0.9 micrometers, where the attenuation is greater than that for longer wavelengths. Modern systems, therefore, operate near the 1.3 and 1.55 micrometers minima shown in Fig 8.13. At these wavelengths, lasers can be made by using indium gallium arsenide or indium gallium arsenide phosphide grown on indium phosphide, and detectors can be made of the same materials, see Fig 8.8. Multimode fibers are larger, 25 micrometers in diameter, than single-mode fibers, 5 micrometers, and transmit a coherent laser beam. By forming numerous optical fibers into a bundle, with an appropriate jacket for mechanical strength, an enormous amount of information can be transmitted over long distances too. Depending upon the losses in the fibers, repeater stations may be required periodically along the path. Thus, many photodetectors and laser sources are required in a fiber optic system. Semiconductor device development, including appropriate binary, ternary, and quaternary compounds for both emitters and detectors, is therefore crucial to the successful implementation of such optical communication systems. A schematic of a fiber optic transmission system is shown in Fig 8.14. What composition X of aluminum X gallium 1X arsine would emit red light at 680 nanometers? What composition of gallium arsenide 1X phosphide X? The band gap e.g., electrovolts, equal 124/L, micrometers, equal 124/068 equal 1.82 electrovolts. From Fig 3.6, we get aluminum 0.32 gallium 0.68 arsine. From Fig 8.10, we get gallium arsenide 0.68 phosphide 0.32. Figure 8.14 schematic of a fiber optic communication system illustrating the transmission of analog signals, such as those in telephony or TV. After the signal is converted to a digital electrical signal, it is used to modulate the laser light output as light pulses that are transmitted down the fiber, with periodic amplification of the signal with repeaters to compensate for fiber loss. Switching circuits route signals appropriately. After the optical signal is transformed to an electrical output by a photodetector and a low-noise preamplifier, LNA, it is converted to an analog signal, once distortions of the digital signals due to propagation through the fiber have been corrected with the use of a regenerator. The word laser is an acronym for light amplification by stimulated emission of radiation, which sums up the operation of an important optical and electronic device. The laser is a source of highly directional, monochromatic, coherent light, and as such it has revolutionized some long-standing optical problems and has created some new fields of basic and applied optics. The light from a laser, depending on the type, can be a continuous beam of low or medium power, or it can be a short burst of intense light delivering millions of watts. Light has always been a primary communications link between humans and the environment, but until the invention of the laser, the light sources available for transmitting information and performing experiments were generally neither monochromatic nor coherent, and were of relatively low intensity. Thus the laser is of great interest in optics, but it is equally important in optoelectronics, particularly in fiber optic communications. The last three letters in the word laser are intended to imply how the device operates, by the stimulated emission of radiation. In Chapter 2 we discussed the emission of radiation when excited electrons fall to lower energy states, but generally, these processes occur randomly and can therefore be classed as spontaneous emission. This means that the rate at which electrons fall from an upper level of energy E2 to a lower level E1 is at every instant proportional to the number of electrons remaining in E2, the population of E2. Thus if an initial electron population in E2 were allowed to decay, we would expect an exponential emptying of the electrons to the lower energy level, with a mean decay time describing how much time an average electron spends in the upper level. An electron in a higher or excited state need not wait for spontaneous emission to occur, however, if conditions are right, it can be stimulated to fall to the lower level and emit its photon in a time much shorter than its mean spontaneous decay time. The stimulus is provided by the presence of photons of the proper wavelength. Let us visualize an electron in state E2 waiting to drop spontaneously to E1 with the emission of a photon of energy Hn12 equal E2, E1, Fig 8.15. Now we assume that this electron in the upper state is immersed in an intense field of photons, each having energy Hn12 equal E2, E1, and in phase with the other photons. The electron is induced to drop in energy from E2 to E1, contributing a photon whose wave is in phase with the radiation field. If this process continues and other electrons are stimulated to emit photons in the same fashion, a large radiation field can build up. This radiation will be monochromatic since each photon will have an energy of precisely Hn12 equal E2, E1 and will be coherent, because all the photons released will be in phase and reinforcing. This process of stimulated emission can be described quantum mechanically to relate the probability of emission to the intensity of the radiation field. Without quantum mechanics we can make a few observations here about the relative rates at which the absorption and emission processes occur. Let us assume the instantaneous populations of E1 and E2 to be N1 and N2, respectively. We know from earlier discussions of distributions and the Boltzmann factor that at thermal equilibrium the relative population will be if the two levels contain an equal number of available states. The negative exponent in this equation indicates that N2 v N1 at equilibrium, that is, most electrons are in the lower energy level as expected. If the atoms exist in a radiation field of photons with energy h N12, such that the energy density of the field is T, N12, 3, then stimulated emission can occur along with absorption and spontaneous emission. Figure 8.15 stimulated transition of an electron from an upper state to a lower state, with accompanying photon emission. Figure 8.16 balance of absorption and emission in steady state, A, stimulated emission, B, absorption, C, spontaneous emission. The rate of stimulated emission is proportional to the instantaneous number of electrons in the upper level N2 and to the energy density of the stimulating field T, N12. Thus we can write the stimulated emission rate as B21 N2T, N12, where B21 is a proportionality factor. The rate at which the electrons in E1 absorb photons should also be proportional to T, N12, and to the electron population in E1. Therefore, the absorption rate is B12 N1T, N12, where B12 is a proportionality factor for absorption. Finally, the rate of spontaneous emission is proportional only to the population of the upper level. Introducing still another coefficient, we can write the rate of spontaneous emission as A21 N2. For steady state the two emission rates must balance the rate of absorption to maintain constant populations N1 and N2, Fig 8.16. This relation was described by Einstein, and the coefficients B12, A21, B21 are called the Einstein coefficients. We notice from EQ 8.8a, that no energy density T is required to cause a transition from an upper to a lower state. Spontaneous emission occurs without an energy density to drive it. The reverse is not true, however. Exciting an electron to a higher state, absorption, requires the application of energy, as we would expect thermodynamically. At equilibrium, the ratio of the stimulated to spontaneous emission rates is generally very small, and the contribution of stimulated emission is negligible. With a photon field present. As EQ 8.8b indicates, the way to enhance the stimulated emission over spontaneous emission is to have a very large photon field energy density R, N12. In the laser, this is encouraged by providing an optical resonant cavity, in which the photon density can build up to a large value through multiple internal reflections at certain frequencies, n. Similarly, to obtain more stimulated emission than absorption we must have N2/N1. The radiation field, we must have a way of maintaining more electrons in the upper level than in the lower level. This condition is quite unnatural, since EQ 8.7 indicates that N2/N1 is less than unity for any equilibrium case. Because of its unusual nature, the condition N27/N1 is called population inversion. It is also referred to as a condition of negative temperature. This rather startling terminology emphasizes the non-equilibrium nature of population inversion, and refers to the fact that the ratio N2/N1 in EQ 8.7 could be larger than unity only if the temperature were negative. Of course, this manner of speaking does not imply anything about temperature in the usual sense of that word. The fact is that EQ 8.7 is a thermal equilibrium equation and cannot be applied to the situation of population inversion without invoking the concept of negative temperature. In summary, EQs 8.8b and 8.9 indicate that if the photon density is to build up through a predominance of stimulated emission over both spontaneous emission and absorption, two requirements must be met. We must provide, 1. An optical resonant cavity to encourage the photon field to build up and, 2. A means of obtaining population inversion. An optical resonant cavity can be obtained using reflecting mirrors to reflect the photons back and forth, allowing the photon energy density to build up. One or both of the end mirrors are constructed to be partially transmitting so that a fraction of the light will leak out of the resonance system. This transmitted light is the output of the laser. Of course, in designing such a laser one must choose the amount of transmission to be a small perturbation on the resonance system. The gain in photons per pass between the end plates must be larger than the transmission at the ends, scattering from impurities, absorption, and other losses. The arrangement of parallel plates providing multiple internal reflections is similar to that used in the Fabry-Perot interferometer, for thus the reflecting ends of the laser cavity are often referred to as Fabry-Perot faces. As Fig 817 indicates, light of a particular frequency can be reflected back and forth within the resonant cavity in a reinforcing, coherent, manner if an integral number of half wavelengths fit between the end mirrors. Thus the length of the cavity for stimulated emission must be Figure 817 resonant modes within a laser cavity, where m is an integer. In this equation L is the photon wavelength within the laser material. If we wish to use the wavelength L0 of the output light in the atmosphere, often taken as the vacuum value, the index of refraction n of the laser material must be considered. In practice, L greater than L, and EQ 810, is automatically satisfied over some portion of the mirror. An important exception occurs in the vertical cavity surface emitting lasers discussed in section 8.4.4, for which the cavity length is comparable to the wavelength. There are ways of obtaining population inversion in the atomic levels of many solids, liquids, and gases, and in the energy bands of semiconductors. Thus the possibilities for laser systems with various materials are quite extensive. An early laser system used a ruby rod. In gas lasers, electrons are excited to metastable levels in molecules to achieve population inversion. These are interesting and useful laser systems, but in view of our emphasis on semiconductor devices in this book, we will move to the description of semiconductor lasers. The laser became an important part of semiconductor device technology in 1962 when the first p-n junction lasers were built in gallium arsenide, infrared, 5 and gallium arsenide phosphide, visible. 6. We have already discussed the incoherent light emission from p-n junctions, LEDs, generated by the spontaneous recombination of electrons and holes injected across the junction. In this section we shall concentrate on the requirements for population inversion due to these injected carriers and the nature of the coherent light from p-n junction lasers. These devices differ from solid, gas, and liquid lasers in several important respects. Junction lasers are remarkably small, typically on the order of 0.1 * 0.1 * 0.3 mm, they exhibit high efficiency, and the laser output is easily modulated by controlling the junction current. Semiconductor lasers operate at low power compared, for example, with ruby or carbon dioxide lasers. On the other hand, these junction lasers compete with helium-neon lasers in power output. Thus the function of the semiconductor laser is to provide a portable and easily controlled source of low-power coherent radiation. They are particularly suitable for fiber optic communication systems, section 8.2.2. Population inversion at a junction. If a p-n junction is formed between degenerate materials, the bands under forward bias appear as shown in Fig 818. If the bias, and thus the current, is large enough, electrons and holes are injected into and across the transition region in considerable concentrations. As a result, the region about the junction is far from being depleted of carriers. This region contains a large concentration of electrons within the conduction band and a large concentration of holes within the valence band. If these population densities are high enough, a condition of population inversion results, and the region about the junction over which it occurs is called an inversion region 7. Population inversion at a junction is best described by the use of the concept of quasi-Fermi levels, section 4.3.3. Since the forward biased condition of Fig 818 is a distinctly non-equilibrium state, the equilibrium equations defining the Fermi level are not applicable. In particular, the concentration of electrons in the inversion region, and for several diffusion lengths into the p material, is larger than equilibrium statistics would imply, the same is also true for the injected holes in the N material. We can use EQ 415 to describe the carrier concentrations in terms of the quasi-Fermi levels for electrons and holes in steady state. Thus, Figure 818 band diagram of a p-n junction laser under forward bias. The cross-hatched region indicates the inversion region at the junction. Using EQs 812a and b, we can draw Fn and Fp on any band diagram for which we know the electron and hole distributions. For example, in Fig 818, Fn in the neutral N region is essentially the same as the equilibrium Fermi level EFn. This is true to the extent that the electron concentration on the N side is equal to its equilibrium value. However, since large numbers of electrons are injected across the junction, the electron concentration begins at a high value near the junction and decays exponentially to its equilibrium value Np deep in the p material. Therefore, Fn drops from EFn as shown in Fig 818. We notice that, deep in the neutral regions, the quasi-Fermi levels are essentially equal. The separation of Fn and Fp at any point is a measure of the departure from equilibrium at that point. Obviously, this departure is considerable in the inversion region, since Fn and Fp are separated by an energy greater than the band gap, Fig 819. Unlike the case of the two-level system discussed in section 8.3, the condition for population inversion in semiconductors must take into account the distribution of energies available for transitions between the bands. The basic definition of population inversion holds for dominance of stimulated emission between two energy levels separated by energy Hn. The electron population of the upper level must be greater than that of the lower level. The unusual aspect of a semiconductor is that bands of levels are available for such transitions. Population inversion obviously exists for transitions between the bottom of the conduction band EC and the top of the valence band EV in Fig 819. In fact, transitions between levels in the conduction band up to Fn and levels in the valence band down to Fp take place under conditions of population inversion. For any given transition energy Hn in a semiconductor, population inversion exists when, for band-to-band transitions, the minimum requirement for population inversion occurs for photons with Figure 819 expanded view of the inversion region. Figure 820 variation of the inversion region width with forward bias. When Fn and Fp lie within their respective bands, as in Fig 819, stimulated emission can dominate over a range of transitions, from Hn equal, Fn, Fp, to Hn equal Eg. As we shall see below, the dominant transitions for laser action are determined largely by the resonant cavity and the strong recombination radiation occurring near Hn equal Eg. In choosing a material for junction laser fabrication, it is necessary that electron-hole recombination occur directly, rather than through trapping processes such as are dominant in silicon or germanium. Gallium arsenide is an example of such a direct semiconductor. Furthermore, we must be able to dope the material N-type or P-type to form a junction. If an appropriate resonant cavity can be constructed in the junction region, a laser results in which population inversion is accomplished by the bias current applied to the junction, Fig 820. Emission spectra for p-n junction lasers. Under forward bias, an inversion layer can be obtained along the plane of the junction, where a large population of electrons exists at the same location as a large hole population. A second look at Fig 819 indicates that spontaneous emission of photons can occur due to direct recombination of electrons and holes, releasing energies ranging from approximately Fn, Fp to Eg. That is, an electron can recombine over an energy from F to Fp, yielding a photon of energy Hn equal Fn, Fp, or an electron can recombine from the bottom of the conduction band to the top of the valence band, releasing a photon with Hn equal Ec, Ev equal Eg. These two energies serve as the approximate outside limits of the laser spectra. The photon wavelengths which participate in stimulated emission are determined by the length of the resonant cavity as in EQ 810. Figure 8.21 illustrates a typical plot of emission intensity versus photon energy for a semiconductor laser. At low current levels, Fig 8.21a, a spontaneous emission spectrum containing energies in the range Eg6Hn6, Fn, Fp, is obtained. As the current is increased to the point that significant population inversion exists, stimulated emission occurs at frequencies corresponding to the cavity modes as shown in Fig 8.21b. These modes correspond to successive numbers of integral half wavelengths fitted within the cavity, as described by EQ 810. Finally, at a still higher current level, a most preferred mode or set of modes will dominate the spectral output, Fig 821c. This very intense mode represents the main laser output of the device. The output light will be composed of almost monochromatic radiation superimposed on a relatively weak radiation background, due primarily to spontaneous emission. The separation of the modes in Fig 821b is complicated by the fact that the index of refraction N for gallium arsenide depends on wavelength L. From EQ 810, we have Figure 821 light intensity versus photon energy Hn for a junction laser, A. Incoherent emission below threshold, B. Laser modes at threshold, C. Dominant laser mode above threshold. The intensity scales are greatly compressed from A to B to C. If M, the number of half wavelengths in L, is large, we can use the derivative to find its rate of change with L0. Now reverting to discrete changes in M and L0, we can write. If we let M equal -1, we can calculate the change in wavelength L0 between adjacent modes, i.e., between modes M and M1. The basic semiconductor laser. To build a p-n junction laser, we need to form a junction in a highly doped, direct semiconductor, gallium arsenide, for example, construct a resonant cavity in the proper geometrical relationship to the junction, and make contact to the junction in a mounting which allows for efficient heat transfer. The first lasers were built as shown in Fig 822. Beginning with a degenerate N-type sample, a p region is formed on one side, for example by diffusing zinc into the N-type gallium arsenide. Since zinc is in column 2 of the periodic table and is introduced substitutionally on gallium sites, it serves as an acceptor in gallium arsenide. Therefore, the heavily doped zinc diffused layer forms a P+ region, Fig 822b. At this point we have a large area planar p-n junction. Next, grooves are cut or etched along the length of the sample as in Fig 822c, leaving a series of long p regions isolated from each other. Figure 822 fabrication of a simple junction laser, A. Degenerate N-type sample, B. Diffused p layer, C. Isolation of junctions by cutting or etching, D. Individual junction to be cut or cleaved into devices, E. Mounted laser structure. These p-n junctions can be cut or broken apart, Fig 822d, and then cleaved into devices of the desired length. At this point in the fabrication process, the very important requirements of a resonant cavity must be considered. It is necessary that the front and back faces, Fig 822e, be flat and parallel. This can be accomplished by cleaving. If the sample has been oriented so that the long junctions of Fig 822d are perpendicular to a crystal plane of the material, it is possible to cleave the sample along this plane into laser devices, letting the crystal structure itself provide the parallel faces. The device is then mounted on a suitable header, and contact is made to the P region. Various techniques are used to provide adequate heat sinking of the device for large forward current levels. Heterojunction lasers. The device described above was the first type used in the early development of semiconductor lasers. Since the device contains only one junction in a single type of material, it is referred to as a homojunction laser. To obtain more efficient lasers, and particularly to build lasers that operate at room temperature, it is necessary to use multiple layers in the laser structure. Such devices, called heterojunction lasers, can be made to operate continuously at room temperature to satisfy the requirements of optical communications. An example of a heterojunction laser is shown in Fig 823. In this structure, the injected carriers are confined to a narrow region so that population inversion can be built up at lower current levels. The result is a lowering of the threshold current at which laser action begins. Carrier confinement is obtained in this single heterojunction laser by the layer of aluminum gallium arsenide grown epitaxially on the gallium arsenide. Indium gallium arsenide. The laser action occurs primarily on the P side of the junction due to a higher efficiency for electron injection than for hole injection. In a normal p-n junction, the injected electrons diffuse into the P material such that population inversion occurs for only part of the electron distribution near the junction. Figure 823. Use of a single heterojunction for carrier confinement in laser diodes. A. Aluminum gallium arsenide heterojunction grown on the thin p-type gallium arsenide layer. B. Band diagrams for the structure of A, showing the confinement of electrons to the thin p region under bias. However, if the p material is narrow and terminated in a barrier, the injected electrons can be confined near the junction. In Fig 823a, an epitaxial layer of p-type aluminum gallium arsenide, e.g. equal to electron volts, is grown on top of the thin p-type gallium arsenide region. The wider band gap of aluminum gallium arsenide effectively terminates the p-type gallium arsenide layer, since injected electrons do not surmount the barrier at the gallium arsenide aluminum gallium arsenide heterojunction, Fig 823b. As a result of the confinement of injected electrons, laser action begins at a substantially lower current than for simple p-n junctions. In addition to the effects of carrier confinement, the change of refractive index at the heterojunction provides a waveguide effect for optical confinement of the photons. A further improvement can be obtained by sandwiching the active gallium arsenide layer between two aluminum gallium arsenide layers, Fig 824. This double heterojunction structure further confines injected carriers to the active region, and the change in refractive index at the gallium arsenide aluminum gallium arsenide boundaries helps to confine the generated light waves. In the double heterojunction laser shown in Fig 824b, the injected current is restricted to a narrow stripe along the lasing direction, to reduce the total current required to drive the device. This type of laser was a major step forward in the development of lasers for fiber optic communications. Separate confinement and graded index channels. One of the disadvantages of the double heterostructure laser shown in Fig 824 is the fact that the carrier confinement and the optical waveguiding both depend on the same heterojunctions. It is much better to optimize these two functions by using a narrow confinement region for keeping the carriers in a region of high recombination, and a somewhat wider optical waveguide region. In Fig 825a we show a separate confinement laser in which the width of the optical waveguiding region, W, is optimized by using the refractive index step at a separate heterojunction from that used to confine the carriers. Figure 824a double heterojunction laser structure. A. Multiple layers used to confine injected carriers and provide waveguiding for the light. B. A stripe geometry designed to restrict the current injection to a narrow stripe along the lasing direction. One of many methods for obtaining the stripe geometry, this example is obtained by proton bombardment of the unshaded regions in B, which converts the gallium arsenide and aluminum gallium arsenide to a semi-insulating form. For example, in the gallium arsenide, aluminum X gallium 1, X arsenide system, the optical confinement, waveguiding, occurs at a boundary with much larger composition X, and therefore smaller refractive index, than is the case for the carrier confinement barrier. By grading the composition of the aluminum gallium arsenide, it is possible to obtain even better waveguiding. Figure 825 separate confinement of carriers and waveguiding. A. Use of separate changes in aluminum gallium arsenide alloy composition to confine carriers in the region, D, of the smallest band gap and to obtain waveguiding at the larger step in the refractive index. B. Grading the alloy composition, and therefore the refractive index, for better waveguiding and carrier confinement. For example, in Fig 825b, a parabolic grading of the refractive index leads to a waveguide within the laser analogous to that shown in Fig 812 for a fiber. This graded index separate confinement heterostructure, GRINSCH, laser also provides built-in fields for better electron confinement. Vertical cavity surface emitting lasers, VCSELs. There are advantages to laser structures in which light is emitted normal to the surface, including ease of device testing on the wafer before packaging. An interesting approach is the VCSEL, in which the cavity mirrors are replaced by DBRs, which use many partial reflectors spaced to reflect light constructively. DBRs can be grown by MBE or OMVPE. In Fig 826, the bottom DBR mirror of a VCSEL is composed of many alternating layers of aluminum arsenide and gallium arsenide with thickness 1/4 of a wavelength in each material. The top mirror is composed of deposited dielectric layers, alternating zinc selenide and magnesium fluoride. Current is funneled into the active region from the top contact by using an oxide layer achieved by laterally oxidizing an aluminum gallium arsenide layer to form an aluminum oxide. The active region of the laser employs indium gallium arsenide quantum wells, and the gallium arsenide cavity between the two DBRs is 1 wavelength long. The VCSEL can be made with much shorter cavity length than other structures, and as a result of EQ 816, the laser modes are widely separated in wavelength. Thus single-mode laser operation is more easily achieved with the VCSEL. Lasing can be achieved at very low current, below 50 microamps, with this device. Materials for semiconductor lasers. We have discussed the properties of the junction laser largely in terms of gallium arsenide and aluminum gallium arsenide. However, as discussed in section 8.2.2, the indium gallium arsenide phosphide/indium phosphide system is particularly well suited for the type of lasers used in fiber optic communication systems. Lattice matching, section 1.4.1, is important in creating heterostructures by epitaxial growth. The fact that the aluminum gallium arsenide band gap can be varied by choice of composition on the column 3 sublattice allows the formation of barriers and confining layers such as those shown in section 8.4.4. Figure 826 schematic cross-section of oxide-confined vertical cavity surface-emitting laser diode. The quaternary alloy indium gallium arsenide phosphide is particularly versatile in the fabrication of laser diodes, allowing considerable choice of wavelength and flexibility in lattice matching. By choice of composition, lasers can be made in the infrared range 1.3 to 1.55 micrometers required for fiber optics. Since 4 components can be varied in choosing an alloy composition, indium gallium arsenide phosphide allows simultaneous choice of energy gap, and therefore emission wavelength, and lattice constant, for lattice-matched growth on convenient substrates. In many applications, however, other wavelength ranges are required for laser output. For example, the use of lasers in pollution diagnostics requires wavelengths farther in the infrared than are available from indium gallium arsenide phosphide and aluminum gallium arsenide. In this application, the ternary alloy lead tin telluride provides laser output wavelengths from about 7 micrometers to more than 30 micrometers at low temperatures, depending on the material composition. For intermediate wavelengths, the indium gallium antimony system can be used. Materials chosen for the fabrication of semiconductor lasers must be efficient light emitters and also be amenable to the formation of p-n junctions and in most cases the formation of heterojunction barriers. These requirements eliminate some materials from practical use in laser diodes. For example, semiconductors with indirect band gaps are not sufficiently efficient light emitters for practical laser fabrication. The 2,6 compounds, on the other hand, are generally very efficient at emitting light, but junctions are difficult to form. By modern crystal growth techniques such as MBE and MOVPE, it is possible to grow junctions in zinc sulfide, zinc selenide, zinc telluride, and alloys of these materials, using nitrogen as the acceptor. Lasers can be made in these materials which emit in the green and blue-green regions of the spectrum. In recent years, much progress has been made in the growth of large bandgap semiconductors using gallium nitride, and its alloys with indium nitride and aluminum nitride. The indium aluminum gallium nitride system has direct band gaps over the entire alloy composition range, and hence offers very efficient light emission. Band gaps range from about 2 electron volts for indium nitride to 3.4 electron volts for gallium nitride and 5 electron volts for aluminum nitride. This covers the wavelength range from about 620 nanometers to about 248 nanometers, which is from blue to ultraviolet. The resurgence of interest in this field was triggered by the work of Nakamura at Nikkei Corporation in Japan, who demonstrated very high efficiency blue light emitting diodes, LEDs, in gallium nitride. Two of the problems that had stymied progress in this field since pioneering work by Pankov in the 1970s was the absence of a suitable substrate having sufficient lattice match with gallium nitride, and the inability to achieve p-type doping in the semiconductor. Gallium nitride bulk crystals cannot be grown easily because of the high vapor pressure of the nitrogen-bearing precursor, generally ammonia. This requires growth at high temperature and pressure. This precludes using bulk gallium nitride wafers as substrates for epitaxial growth. However, epitaxial layers can be grown on other substrates with reasonable success, in spite of the lattice mismatch. Gallium nitride exists in the cubic zinc blende form, which is the preferred structure, as well as the hexagonal wurtzite form. It was demonstrated recently that cubic gallium nitride could be grown heteroepitaxially on sapphire, even though it is not lattice matched to gallium nitride. In fact, sapphire does not even have a cubic crystal structure, it is hexagonal. The lattice constant of gallium nitride is about 4.5 angstroms, while that of sapphire is 4.8 angstroms, which is a huge lattice mismatch. Contrary to what would normally be expected, however, high-quality epitaxial gallium nitride films can be grown on sapphire by MOCVD using ammonia and trimethyl gallium as the precursors. One possible reason for the high quality of the films, as evidenced by blue LEDs and short wavelength lasers fabricated in these nitrides, is that these large bandgap semiconductors have very high chemical bond strengths. As discussed in section 8.2.1, the addition of into gallium nitride results in lower bandgap in rich regions, which provide sites for radiative recombination, minimizing the loss of carriers at dislocations. Another breakthrough required in the nitrides was the ability to achieve high p-type doping so that p-n junctions could be formed. It has been demonstrated that Mg, which is a column 2 element, doping of MOCVD films, followed by high-temperature annealing, can be used to achieve high acceptor concentrations in these systems. Short-wavelength emitters such as ultraviolet blue semiconductor lasers are important for storage applications such as digital versatile discs, DVDs, which are higher-density versions of compact discs, CDs. The storage density on these discs is inversely proportional to the square of the laser wavelength that is used to read the information. Thus reducing the laser wavelength by a factor of 2 leads to a 4-fold increase of storage density. Such an increased storage capacity opens up entirely new applications for DVDs that were not possible previously with conventional CDs, for example, the storage of full-length movies. A recent example of success in this rapidly progressing field is a 417 nanometer semiconductor laser made with indium gallium nitride multi-quantum well heterostructures. Quantum cascade lasers. The lasers described above are bipolar devices involving interband transitions. Electrons in the conduction band recombine with holes in the valence band, and photons are emitted at an energy determined by the bandgap. This limits laser operation to direct bandgap materials for reasons discussed in Chapter 4. The quantum cascade laser, QCL, on the other hand, involves unipolar operation based on intersubband transitions in a series of coupled quantum wells, separated by superlattices, Fig 827. As discussed in Chapter 1 and 3, quantum wells and superlattices are made of semiconductor heterostructures with layer thicknesses comparable to or smaller than the de Broglie wavelengths of the electrons. In quantum wells, one gets confinement in one direction, but plane wave states in the other two directions. This leads to subband levels shown in Fig 827. Figure 827 Quantum Cascade Laser based on 3-level system in conduction band. Photons are emitted each time there is a transition from level 3 to 2 in the staircase of stages. Carriers are injected from level 1 of one stage to level 3 of the next stage through a superlattice, SL, miniband. By carefully designing the quantum well structure in a QCL, one can design a 3-state system, Fig 827. By biasing the QCL, carriers are injected from the left into state 3, creating a population inversion between states 3 and 2. There is a relatively thick tunnel barrier between states 3 and 2 in order to allow the population inversion. However, the barrier must be narrow enough to allow overlap of the wave functions in states 3 and 2, and allow transitions between these levels and allow lasing. Photons in the QCL are emitted upon transition to state 2. Carriers in state 2 are closely coupled by a thin tunnel barrier to state 1, and are immediately removed to this state, so that the population inversion between states 3 and 2 can be maintained. Carriers in state 1 are subsequently injected to state 3 in the next stage of the QCL through the digitally graded superlattice, SL, and the whole process is repeated, until the current is extracted on the right-hand side of the QCL. It is clear that the number of photons emitted per electron injected depends on the number of these energy staircases, 1, 2, 3. Since the QCL involves electronic transitions entirely within conduction intersub and quantum well states, it does not require a direct bandgap semiconductor, and the photon energy is not related to the bandgaps of the semiconductors used in the superlattice. Instead, the photon energies are much lower, and are determined by the quantum well design and the sub-band energies. This enables one to generate terahertz radiation in a very important portion of the electromagnetic spectrum between micro/sub-millimeter waves and far infrared, 300 GHz 3 terahertz, where there is a paucity of good sources, leading to the so-called terahertz gap. This frequency range is very useful, for example, for biomolecule and chemical species detection because many molecular transitions are in this frequency range. Summary. The emission and absorption of light by semiconductors gives rise to useful optoelectronic devices. Emission typically occurs in direct bandgap materials. Indirect semiconductors are less optically efficient because they require the involvement of both photons, which carry energy, but little momentum, and phonons, which carry momentum, but little energy. In some optoelectronic devices, electron-hole pairs, EHPs, are generated by the absorption of light. These carriers can be collected as electrical energy in solar cells or photodetectors. Generated electron-hole pairs add to the thermally generated reverse current in diodes, EQ82, from which one can obtain the open circuit voltage or short circuit current in solar cells, a potential renewable source of energy. In photodetectors, there is a trade-off between speed, which requires a short absorption region for a short transit time, and sensitivity, which requires long absorption regions. Clever structures to get both include waveguide photodetectors. One can achieve gain by using avalanche photodiodes, in which impact ionization can increase the number of electron-hole pairs generated for a certain number of absorbed photons. However, this can be at the expense of increased impact ionization noise in photodiodes. Photodiodes, in conjunction with light emitters, are used with optical fibers for fiber optic communication, which is the backbone of the Internet and worldwide communication today. Optical fibers are waveguides that work on the basis of the total internal reflection of light from a low refractive index outer layer to a high refractive index medium, glass. Semiconductors can be used not only to detect photons, but also to emit photons by the recombination of electron-hole pairs in direct bandgap semiconductors. Light emitters can be non-coherent, such as LEDs, or coherent, such as lasers. The color of light depends on the semiconductor, because the photon frequency is proportional to the bandgap, Planck relationship. Lasers are more difficult to make than LEDs, because they require not just electron-hole pairs, but population inversion, i.e., more carriers in the higher energy levels than in the lower ones. This enables stimulated emission of phase-coherent radiation, governed by the Einstein B coefficient, to dominate over phase-incoherent spontaneous radiation, determined by the Einstein A coefficient. Lasers also require an optical cavity to allow the photon field to build up. Light can come out from the side of the cavity, as in edge-emitting lasers, or from the top surface, as in vertical cavity surface-emitting lasers, VCSELs. Double heterostructure lasers are useful because they allow both carrier and photon confinement.